Hello students. So in today's class, we are going to introduce the idea of nonlinear regression functions. So far when we have looked at regression, we have always assumed that the dependent variable, which may be continuous or discrete, is a linear function of the independent variables. But suppose the linear function does not in fact describe the relationship between y's and x's, and there is in fact some nonlinear relationship over there, then we need to take that into account, and that is what we are going to talk about. So we will relax the assumption of there being a linear relationship between y and the independent variables x's, the different x's. So the outline of this lecture will be like this. First, we will generally talk about nonlinear regression functions. Then we will talk about nonlinear functions involving one variable. Then we will look at nonlinear functions involving two or more different variables, where we will talk about the interactions between the variables. And finally, we will look at an application in the California test score data set. So the regression functions so far have been linear in the x's, but a linear approximation is not always a good one. So the multiple regression model can handle regression functions that are non-linear in one or more x. Now one distinction has to be made. Over here, when we are talking of nonlinearity, we are talking of nonlinearity in terms of x's. So y is a function of x, y is some function of x. So far we have assumed y to be a linear function of x, but now we will assume that the x's can take different kinds of functional forms, which will allow y to be defined as a nonlinear function of x. So what are these functional forms? This is what we are going to look at. So the test score STR relation looks linear. Okay, it looks sort of linear. There doesn't seem to be, if you fit a straight line through this, it sort of approximately goes through the middle of the cloud of points. Okay, but let us look at the test score income relationship. So over here, on the x-axis we have the district income. In the previous case, on the x-axis we had the student-teacher ratio. In this case we have the district income, and we have test score on our y-axis. Now what we see is that the cloud of points does not seem to, cannot really be approximated well by a line. So if you draw a line through this cloud of points, what will happen is, on this side there are more number of data. The more over here, the blue line is overestimating the test score for those schools which have low income, which are in low income districts, and the line actually underestimates the test scores of districts which have high levels of income. Okay, so as we can see, at low levels of income, with slight increase in district income, the test scores rise much more sharply. But as it reaches some kind of a threshold, as income rises even further, the test scores do not rise so sharply, and they in fact flatten out. So there is some kind of a differential slope at different levels of income. So there is a nonlinear relationship. So we now define the idea of a nonlinear regression population. So this is what? If a relationship between y and x is nonlinear, the effect on y of a change in x depends on the value of x. So as we can see over here, for low values of x, the effect of a change in x on y is very high. So if you were to in fact fit two different models, two different lines, then this might be a line over here and this might be a line over here. Okay, let me just draw that better using a different color so that it will be clear. So over here this kind of a line may be more appropriate. Okay, so as you can see, the slope is changing in different regimes of x. In this regime of x, the slope is much higher, and in this regime of x, the slope is lower. So with different values of x, the marginal effect of a change in x on y is changing. So this is what we mean when we say that the relationship is non-linear. So effect on y of a change in x depends on the value of x. This value of x is what we are calling as the regime of x. Value of x, that is the marginal effect of on effect of x is not constant, a linear regression is misspecified, and the functional form is wrong. So the estimator of the effect on y of x is biased. In general, it isn't even right on average. What does it mean? That the beta hat that you will estimate, this will be biased. Okay, in that particular case, the beta hat will not be the accurate beta hat or the true beta hat. It will be either more than what you estimate or less than what you estimate, depending on the regime of x. So the solution is to estimate a regression function that is non-linear in x. So you actually allow the slope to change for different values of x. So the general nonlinear population regression function is specified as yi is a function of x1i, x2i, xki. Here x1 stands for the first variable, x2 stands for the second variable, and xk stands for the kth independent variable, and I stands for each of the observations, and there are n observations. Here the assumptions are as before. The expected value of the error, you fit such a model such that the error that is left over overall, the mean error will be 0. Expected value of error given the different values of the independent variables will be the same, implies that f is the conditional expectation of y given the x's. x1i to xki and yi are IID. This is the same assumption as before. Big outliers are rare. That is the same idea. Okay, and there is no perfect multicollinearity. That is that each of the independent variables are not an exact linear combination of any of the independent variables is not an exact linear combination of the other independent variables. So now you cannot directly get just the marginal change. What is the marginal effect of x1? What is the marginal effect of x1 over yi in the nonlinear case is not just given by beta 1 or beta 2 or whatever, because there is a nonlinear function. So the way we say it is that the change in y is when you change, what is the marginal effect of a change in x1 on y is you put in that plus delta x1 over here, f of x1 plus delta x1 and all the other remain the same, minus f of x1 and all the other remaining the same. So in each of these cases all the other variables are remaining the same, only x1 is changing from x1 to x1 from delta x1, and you look at what is this result of just the marginal change in x1 on y, and that is given as the change in y with a unit change or a marginal change in x1, and this will be defined as the change on y of a unit change in x1. So let us look at how we will look at this. So the expected effect on y of a change in x1 in a nonlinear regression model. Notice that we are now talking about the nonlinear regression model. So we cannot directly, in a linear regression model where you are just stating it as beta 0 plus beta 1 x1 plus beta 2 x2 plus up to beta k xk, then what happens is you can directly say that beta 1 and beta 2 are the marginal effect of one unit change in x1 on the change of y for a unit change in x1. Here you could directly say that. But if it is a non-linear function, then you actually need to put in those values and calculate the y's before and after a unit change in x1, and then the delta y will be the functional value after you have increased x1 by a unit and kept everything else the constant, and also minus what it was before. So that will be, this is formally the change in y. Okay, so the estimator of this unknown population difference in the differences between the predicted values for these two cases. Okay, so suppose f hat x1, x2 up to xk is the predicted value of y based on the estimator f hat of the population regression function, then predicted change in y is f hat of x1 plus delta x1 this minus f hat of this. Why are we using f hat? Because we have not yet defined our nonlinear function, and it will become clear to us what our nonlinear function is and how we can estimate it in a minute. Okay. So nonlinear functions of a single independent variable. We will look at two complementary approaches. There are two ways in which we can introduce nonlinearity in the function. One is by introducing polynomials of x. So polynomials in x, the population, what are polynomials? Basically x square, x cube, these kinds of terms. So you know, any power of x, if you introduce any power of x into the formula, into your specification, so it could be is approximated by a quadratic, cubic or higher degree polynomial. This is a quadratic, this is a cubic, and these are higher degree polynomials. You could include such terms. Okay. Another thing to do is to include y and or x is transformed by taking its logarithm that gives a percentages interpretation. So instead of directly regressing y on x, you could regress log of y on x, or you could regress y on log of x, or you could regress log of y on log of x. So you could basically take a logarithmic transformation on one or both sides, and that actually, as we will see, it can be interpreted in terms of percentage changes in one or in either the independent variable or the dependent variable. Okay, so these are the two different nonlinear transformations that we are going to look at. Okay. So first we will look at polynomials in x. So suppose we approximate the population regression function by a polynomial, and we take the simplest polynomial, that is we take a quadratic function. So beta yi equals to beta 0 plus beta 1 xi plus beta 2 xi square. So in addition to the term xi, you can put xi square. So this is just a linear multiple regression model, except that the regressors are powers of x. Now you may think that you are putting the same variable twice. Okay, you are putting xi and you are putting xi square. So wouldn't this result in perfect multicollinearity? But if you remember, for perfect multicollinearity to happen, x2 has to be a linear combination of x1. Okay, so linear combination of x1 for perfect multicollinearity to happen. But here x2 is not a linear combination of x1, rather x2 is x1 square. So because it is a quadratic transformation of x1, it's not a linear combination. So this including x1 square does not result in perfect multicollinearity. Okay, so that is one doubt that often comes up. So estimation, hypothesis testing, etc. proceeds in the same way as in the multiple regression model using OLS. The coefficients that you interpret, that is what is the meaning of beta 1 and beta 2, when you interpret this, they are difficult to interpret by themselves, but the regression function itself is interpretable. So for instance, if we take the test score income relation, Okay, so the income that we just looked at, that it is in fact a non-linear relationship. So income is the average district income in the ith district, thousands of dollars per capita, and the quadratic specification is test score equals to beta 0 plus beta 1 income I plus beta 2 income whole square plus ui. And the cubic specification will be test score equals to beta 0 plus beta 1 income I plus beta 2 income I whole square, plus you now also include a cubic term which is beta 3 income I whole cube. Okay, you don't know which one of these specifications will be right, but if you do a quadratic specification, this is what it will look like, and if you do a cubic specification, this is what it will look like. So, if you estimate the quadratic specification, if you put in a variable, so what you do is you take the you take your independent variable and you create another variable which is the square of the previous independent variable, and you include that squared variable into your regression equation. Now what happens if you include the squared variable? Look at this. You have some beta coefficients. The t statistic associated with this is, the magnitude of the t statistic is high, the p values are low. Okay, so that means in fact it is good to include this squared variable, and if you so if you test the null hypothesis of linearity against the alternative that the regression function is quadratic, you can test the null hypothesis that in fact it is better to include a non-linear term in your regression. So if you get this 607.3 plus 3.85 income. So if you look at your numbers, this is 3.85 over here, and this is minus 0.04 income square. Okay, so that is what you are getting over here. You get 3.85 income minus 0.04 income square, and these are the associated standard errors with that, and both of them are statistically significant. Now if you were to actually plot this nonlinear line, you will get a curve like this, which as you can see seems to fit the data much better. What does it mean by it fits the data? That is, it goes through the middle of the cloud of points. Okay, that is what your aim is. You want to estimate the typical change in test score with a change in income. So you see that this is actually fitting your data better. Now, how do you compute the effects for different values of x? So now remember that it is not that your you get a constant slope which is same no matter what value of x you take. So over here you have to take different values of x. So suppose you take x at 5,000, initial x was $5,000 per capita and the final x goes to $6,000. So what happens if the district income changes from $5,000 per capita to $6,000 per capita? So basically you are comparing one district which has income of $5,000 per capita to another district which has income of $6,000 per capita, and you are trying to look at the changes in test scores between these two districts. So what you do is you put in these values. So in the district with higher income, this is what your estimated test score will be: 607.3 plus 3.85 into 6. Income is in $1,000 per capita, that is the unit, minus 0.0423 into 6 square because income square, minus what is it in the other district which has lower income per capita, that is 5 minus 0.0423 into 5 square. So see that the coefficients remain the same in both cases, only the value of the income is changing from here from say 5 to 6. What is the expected change in test scores between these two districts? The expected change in test scores is 3.4. Okay, so the richer district, the students do better in their test scores. predicted effect for different values of x. So now if income, so now you will see that the marginal effects change depending upon which value of x you are looking at. So if your x changes from, if your per capita income changes from $5,000 to $6,000, your change in test score is 3.4. If it changes from $25,000 to $26,000 per capita, your change in test score is smaller. It is 1.7. As we said before, if it reaches a certain threshold of income, after that any additional change in income does not result in so much of a difference in test score. So it is 1.7. And if the level of income changes from 45 to 46, in each of these cases the change is just $1,000 per capita. 5 to 6, 25 to 26, 45 to 46, in each case the change is only $1,000 per capita. But as you can see, because the slopes are not constant, the test score is changing by differing amounts. So the effect of a change in income is greater at lower income than high income levels, perhaps a declining marginal benefit of an increase in school budgets. Okay, what is the effect of a change from 65 to 66? Basically, since we don't have data for that level, and since we are not assuming a constant slope, it is better not to extrapolate outside the range of the data. So now we estimate the cubic specification and we include a cubic term. So as you can see, the cubic term has a very small beta coefficient, and while it is statistically significant, but the level of significance is somewhat smaller. So actually including the cubic term may not be actually increasing your model fit by that much. Okay, so now suppose you want to test the null hypothesis of linearity against the alternate hypothesis that the population regression is quadratic and or cubic. That is, it is a polynomial of degree up to 3. So basically what we are saying is, if you have a nonlinear regression function, that is y is equal to beta 0 plus beta 1 x1 plus beta 2 x1 square plus beta 3 x1 cube. So this is your unrestricted regression, and your other regression is y equals to beta 0 plus beta 1 x1. So you are in this regression, in the restricted one, you are assuming that the beta 2 and beta 3 are both equal to 0. Okay, so this is a joint hypothesis you are testing. So population coefficients on income square, your null hypothesis is population coefficients on income square, which over here is beta 2 hat, and income cube, which over here is beta 3 hat, both are equal to 0, and this is the null hypothesis. Now if any of these is not equal to 0, then you can reject your null hypothesis that both of them are equal to 0. So if beta 2 hat is not equal to 0, or beta 3 hat is not equal to 0, or both of them are not equal to 0, in any of these three cases, you reject the null hypothesis that they are both equal to 0 and that your function is linear. Okay, so if you don't reject this null hypothesis, then you can say that actually your function is non-linear in reality. So test, you can use this command in Stata, test average income 2 and average income 3, and what you get, your F statistic over here is 37.69. So you reject the null hypothesis because your p values are very small. You reject the null hypothesis. It is rejected at the 1% significant level against the alternative that it is a polynomial of up to degree 3. Okay, so this is how you can test the hypothesis that whether your data is actually nonlinear or not, or your nonlinear regression function is the correct one to use or not. So to summarize, the polynomial regression functions, or how you estimate, you specify it in as you see fit. You include those powers of those independent variables of which you think your dependent variable may be a nonlinear function. You include the quadratic powers or the cubic powers. You estimate by OLS. The coefficients themselves have complicated interpretations. To interpret the estimated regression function, you plot predicted values as a function of x, compute predicted del y by del x at different values of x, and hypothesis concerning degree r, that is polynomial to what degree, can be tested by T and F tests on the appropriate blocks of variables. So should you choose only a quadratic term, or should you choose a cubic term? This you can conduct F tests, or you can do T test for those particular terms, and you can act accordingly.